The wind cut different in northern Minnesota. Samuel Forsyth learned that his first winter of 1882, when frost formed inside his cabin walls, and his water bucket froze solid 3 feet from his fireplace. He had built his hearth exactly the way every settler in the lake and pine country was told to build it. Wide walk-in opening, 4 feet high by 4 feet wide, big enough for massive logs and communal warmth, standard and trusted. By February, he had burned through 3 cords of wood in a single month, and still the cold cut through his walls like the cabin had no fire at all. Across the Great Lakes region, homesteaders were losing the same battle in hearths built by the book and failing by the season. Over the next 2 years, Sam quietly combined techniques from his Scottish father's masonry work and an Ojibwe camp cook's wisdom to build a hearth with an opening barely 2 feet wide that kept his cabin warm all night on half the wood. Neighbors called it foolishly small until the brutal winter of 1884, when Sam slept without blankets while they shivered under 3. What did he understand about heat and draft that every serious builder today ought to know? The settlement of Pine Ridge sat in a natural clearing where the Chippewa River bent through stands of white pine and sugar maple, 40 miles south of Duluth, in the heart of Minnesota's timber country. Winter arrived early in 1882, and by November the thermometer had already dropped to 0 degrees, Fahrenheit 3 times, with wind-driven snow piling against cabin walls in drifts that reached the eaves. The landscape demanded respect. 6 months of bitter cold, frequent blizzards that could last 4 days, and temperatures that regularly plunged 15 degrees below zero when the wind picked up speed across the frozen lakes. Every cabin in Pine Ridge followed the same proven design. The settlement's unofficial building guide, passed down from the lumber company supervisors and reinforced by the territorial homesteading manual, called for generous stone or brick fireplaces with walk-in openings. Most measured 3 to 4 feet high and 4 to 5 feet wide, large enough for a man to step inside and arrange massive oak logs. The logic seemed unshakable. Bigger hearth meant more flame meant more heat, and more heat meant survival through the long, dark months ahead. The wide openings allowed families to gather around the fire for cooking, warmth, and evening light, turning the hearth into the social center of frontier life. But that winter exposed the fatal flaw in the conventional wisdom. Thomas Brennan's cabin, built exactly to specifications with a 4-foot-high opening, suffered from chronic draft problems that left his family shivering despite a roaring fire. The massive opening created what Brennan described as a wind tunnel effect that sucked warm air from the room and sent it straight up the chimney. His interior. Temperature stabilized at only 12 degrees above the outdoor reading, instead of the expected 40 to 50 degree difference that would make the cabin truly livable. On the worst nights, when the wind howled across the clearing, Brennan measured his cabin's inside temperature at 18 degrees Fahrenheit while outside dropped to 0. The Schmidt family faced an even worse problem. Ice formed on the interior surface of their plastered log walls, creating a layer of frost that never melted completely, even when their fire burned bright. Cold air infiltrated around their deep firebox hearth, drawn in by the powerful updraft of the oversized chimney opening. Margaret Schmidt found herself scraping ice from the inside walls every morning, and their 2 youngest children developed persistent coughs that lasted through March. Across Pine Ridge, the fuel consumption told the same dismal story. Families burned through 3 cords of split hardwood in a single month, far exceeding their estimates of 1 cord lasting 6 weeks. At $5 per cord from the local supplier, the winter heating bills threatened to bankrupt homesteaders who had planned their finances around much lower fuel costs. The Anderson family borrowed money to buy additional wood, and the Johnsons rationed their fire to just 4 hours in the evening, leaving their cabin barely above freezing most days. Samuel Forsyth watched these struggles with the calculating eye of someone trained to solve problems through craftsmanship rather than brute force. The son of a Scottish stonemason, Sam had immigrated to Minnesota in 1879 with practical knowledge that most frontier settlers lacked. His father had built hearths in manor houses throughout the Scottish Highlands, where fuel was scarce and efficiency mattered more than impressive size. During his 3 years working as an engineer for the Northern Pine Logging Company, Sam had lived alongside Chippewa workers and learned their approach to winter heating. An elder named White Pine had shown him how a small fire with a large hood above could maintain steady heat through the night using a fraction of the wood that white settlers consumed. When Pine Ridge held its monthly community meeting in February, Sam stood before his neighbors with a proposal that drew immediate skepticism. He wanted to build his hearth with an opening measuring just 2 feet high by 2.5 feet wide, barely large enough for standard firewood. Even more unusual, he planned to construct a generous smoke chamber above the firebox, creating internal volume that seemed wasteful to men accustomed to straightforward construction. Anders Johansson, a Swedish carpenter who had built 4 cabins in the settlement, laughed openly at Sam's suggestion. "You'll choke that fire before it gets started," Johansson declared. "A hearth that small won't warm anything bigger than a chicken coop." The local supply agent, who sold fireplace stones and iron grates, dismissed Sam's plan as excessive fussing for a frontier shack and warned that departing from proven methods would leave Sam's family freezing when the real cold arrived. The social pressure to conform was intense in a settlement where survival depended on shared knowledge and mutual aid. Frontier communities trusted collective wisdom over individual innovation, especially when that innovation came from someone still considered an outsider. Sam had been in Pine Ridge for only 3 years, and his Scottish accent marked him as different from the Scandinavian and German immigrants who formed the settlement's core population. But Sam possessed something his critics lacked: direct experience with alternative methods that worked. His father's masonry training had taught him that shallow fireboxes with controlled openings could produce more radiant heat than deep caverns that swallowed logs whole. The Chippewa elders' demonstration had shown him how proper smoke management could extend burning time and reduce fuel consumption. While his neighbors relied on assumptions about what should work, Sam had seen evidence of what actually did work in different conditions. That spring, as soon as the ground thawed enough for foundation work, Sam began construction of his experimental hearth. He built the firebox only 8 inches deep, forcing the fire close to the room where its radiant heat could warm the living space directly. The narrow face opening would limit the amount of warm room air that escaped up the chimney, while the large smoke chamber above would capture and redistribute heat that conventional designs lost to the outdoors. The fundamental conflict was now clear. Pine Ridge's established settlers believed that bigger fires and bigger openings produced bigger results. Sam's approach suggested the opposite, that smaller, more controlled fires in properly designed spaces could deliver superior performance with less fuel and greater comfort. The coming winter would test which philosophy deserved to survive on the Minnesota frontier. By February of 1883, Pine Ridge faced the kind of blizzard that tested every assumption about frontier survival. Wind-driven snow arrived with sustained gusts reaching 40 miles per hour, and the temperature plummeted to minus 20 degrees Fahrenheit with wind-chill conditions that made outdoor work impossible for days. The storm provided the perfect laboratory for comparing heating systems, and the results revealed flaws in conventional design that no amount of extra fuel could overcome. Thomas Brennan's standard hearth, with its 4-foot-wide opening, created what engineers would later recognize as a classic draft problem. The massive cavity acted like a chimney within a chimney, generating such powerful updraft that heated room air rushed toward the fireplace and escaped before it could warm the living space. Brennan described the sensation of standing near his fire as feeling the heat on your face while cold air pulled at your back. His family huddled in blankets, even with oak logs blazing continuously, and despite burning a full cord of wood in just 5 days, their cabin's interior temperature never rose above 25 degrees Fahrenheit. The crisis deepened when thermal stress cracked the back wall of Brennan's firebox. The massive opening allowed cold outdoor air to infiltrate around the hearth structure, while heated gases escaped rapidly through the oversized throat. This created severe temperature differentials in the masonry. The fire-facing surface reached over 1,000 degrees, while the back wall dropped below freezing. The limestone blocks split along their natural grain lines, creating gaps that allowed even more cold air to enter the living space. Sam's experimental design faced the same brutal conditions but responded entirely differently. His narrow opening, measuring exactly 2 feet high by 2.5 feet wide, restricted the flow of warm room air up the chimney while maintaining adequate draft for proper combustion. The shallow firebox depth of just 8 inches positioned the burning logs close to the room opening, maximizing radiant heat transfer into the living space rather than allowing it to dissipate in a deep cavity. Above the firebox, Sam had constructed a smoke chamber with approximately 20 cubic feet of interior volume, large enough to slow the velocity of rising gases and allow the masonry walls to absorb heat before the smoke continued up the flue. This chamber acted as a thermal buffer, capturing energy that would otherwise escape directly to the outdoors and radiating it gradually into the cabin throughout the night. The most sophisticated element of Sam's design involved the geometric shaping of the firebox itself. Drawing on his father's Scottish masonry techniques, he angled the side walls outward at 20 degrees from vertical, creating splayed surfaces that reflected radiant heat toward the center of the room instead of absorbing it into the stone mass. The throat above the fire featured a gentle arch that guided rising gases smoothly into the smoke chamber, eliminating the turbulence that reduced draft efficiency in square-cornered designs. White pine, the Chippewa elder who had influenced Sam's thinking, visited during the blizzard to observe the results of combining indigenous winter fire wisdom with European stonework precision. He noted that Sam's hearth maintained steady ember beds for 8 to 10 hours after the last log was added, compared to the 2 to 3 hours typical of conventional designs. The sustained heat came from the smoke chamber's thermal mass, which absorbed energy during active burning and released it slowly as the interior temperature dropped. Sam's field measurements during the 5-day storm revealed the practical advantages of controlled draft and thermal retention. Starting each evening with interior temperatures of 15 degrees Fahrenheit, his cabin reached 50 degrees by midnight using approximately 1 cord of split oak. More importantly, the temperature at 6 o'clock the following morning still registered 45 degrees, demonstrating that the system retained heat through the coldest hours when fires typically died to ash. The contrast with conventional performance was striking. Anders Johansson, whose Swedish carpentry experience had led him to build a traditional deep hearth, burned the same amount of wood but achieved interior temperatures of only 35 degrees by morning. His family required additional blankets and often rekindled their fire at 5 in the morning to make the cabin livable for breakfast preparation. The efficiency difference became measurable in fuel consumption patterns. Sam's system used 1 cord of wood to maintain comfortable heating for 72 continuous hours, while comparable cabins required the same amount of fuel for only 56 hours of equivalent warmth. This represented a 28% improvement in heating efficiency, translating to significant cost savings over the course of a Minnesota winter. The superior performance came from understanding heat transfer principles that frontier building practices had overlooked. Large fireplace openings created convective losses that overwhelmed the radiant benefits of big fires. Cold air infiltration around oversized hearths negated much of the heat gain, while rapid updraft through wide throats carried energy straight out of the building envelope. Sam's design minimized these losses while maximizing heat retention through controlled airflow and thermal mass. Jakob Müller, a German immigrant with European masonry experience, examined Sam's hearth during a break in the storm and recognized techniques that paralleled old-world fireplace design. The shallow firebox and angled side walls resembled methods used in German manor houses, where fuel efficiency mattered more than impressive appearance. Miller noted that Sam had adapted these principles to frontier conditions and materials, creating a hybrid system that combined the best elements of different building traditions. The psychological impact on the settlement was immediate. Families who had endured the blizzard in barely heated cabins could see smoke rising steadily from Sam's chimney while observing that his windows remained free of interior frost. The contrast between his family's comfort and their own suffering made the theoretical arguments about fireplace design suddenly concrete and urgent. When the storm finally cleared, Sam's neighbors found him splitting wood in his shirt sleeves while they bundled in heavy coats, just to venture outside for essential chores. The evidence of his heating system's superiority was undeniable, measured not in abstract principles, but in the practical reality of warmth, fuel savings, and livable indoor conditions during the worst weather Pine Ridge had experienced. In living memory, the winter of 1883 brought a different challenge to Pine Ridge. Erratic temperature swings that tested building envelopes as severely as steady cold. January temperatures fluctuated between 10 below zero and 20 above within single-week periods, while March delivered alternating freeze-thaw cycles that caused log walls to expand and contract repeatedly. Sam observed that his efficient hearth design solved the combustion problem, but revealed secondary issues that conventional wisdom had masked with wasteful fuel consumption. The settlement's log construction method followed standard frontier practice: horizontal logs notched and stacked with clay and moss chinking between courses. This approach worked adequately when fires burned continuously at high output, but Sam's fuel-efficient system exposed how much heat escaped through gaps that opened during temperature fluctuations. His cabin's interior temperature dropped from 45 degrees to 32 degrees overnight, not from hearth problems, but from air infiltration through joints that shifted as the wood moved. Anders Johansson, despite his earlier skepticism about Sam's fireplace design, possessed valuable knowledge about building envelope construction from his Scandinavian background. In Sweden, timber frame buildings incorporated double wall systems to combat harsh winters, and Johansson had adapted these techniques for his own barn construction. He showed Sam how to create an air gap buffer by installing a second layer of rough-cut split logs horizontally behind the exterior siding, leaving a 6-inch cavity between the two wood surfaces. The air gap principle worked by breaking wind-driven infiltration into two separate barriers. The outer layer absorbed the direct impact of wind pressure and precipitation, while the inner wall remained relatively stable because the cavity decoupled it from external forces. Johansson explained that still air trapped between the walls provided insulation value roughly equivalent to 4 inches of solid wood, significantly reducing heat transfer through the building envelope. Sam implemented this double wall technique across the north and west faces of his cabin, where prevailing winds created the greatest infiltration pressure. The construction required splitting additional logs into 4-inch thick planks and mounting them on wooden spacers that maintained the air gap consistently. The labor was considerable, but the thermal benefits became apparent immediately. Interior surfaces of the log walls remained warm to the touch, even when exterior temperatures dropped below zero. White pine contributed a different but complementary insight about thermal mass management. During his years of winter camping in the northern forests, he had learned to position large flat stones behind cooking fires to absorb radiant heat during active burning and release it gradually throughout the night. The stones acted as thermal batteries, storing energy when it was abundant and delivering it when the fire died to coals. Sam adapted this principle by installing limestone slabs measuring approximately 2 feet high by 4 feet wide by 6 inches thick directly behind his firebox, extending into the living space floor and rising 12 inches above hearth level. These stones absorbed radiant energy from the fire at temperatures reaching 1200 degrees Fahrenheit, then slowly released that heat into the cabin over 6 to 8 hours. The thermal mass effect was dramatic. The stones remained warm to the touch until morning, continuing to heat the space long after the last flames disappeared. The positioning of thermal mass required careful calculation. Stones placed too close to the fire absorbed heat rapidly, but also radiated it back toward the flames, reducing combustion efficiency. Stones placed too far away received insufficient energy to store meaningful amounts of heat. Sam determined through trial and observation that 6 inches behind the fire's back wall provided optimal heat absorption while allowing proper air circulation around the burning logs. Beyond thermal storage, Sam recognized that heat distribution within the cabin needed improvement. Traditional hearths sat at floor level, requiring occupants to heat the entire volume of room air before achieving comfortable conditions. Cold air near the floor created convective currents that pulled warmth away from the living zone where people actually sat and slept. Sam's solution involved constructing a raised masonry platform measuring 18 inches high, 4 feet deep, and 6 feet wide that elevated both the hearth and the thermal mass stones. This platform placed the radiant heat source closer to the occupied zone while creating a smaller volume of air that required heating. Family members could sit directly on the warm stone surface or position chairs close enough to benefit from radiant heat without waiting for convective warming of the entire cabin interior. The raised hearth extension also addressed ground-level heat loss that plagued floor-mounted fireplaces. Cold air infiltration along the cabin floor created a thermal sink that absorbed heat from conventional hearths, while frozen ground beneath the building conducted energy downward through the foundation. By elevating the heat source above this cold zone, Sam reduced parasitic losses and improved the effective heating efficiency of his already optimized combustion system. The integrated approach of envelope sealing, thermal mass, and heat positioning created synergistic benefits that exceeded the sum of individual improvements. The air gap walls reduced heat loss through infiltration by approximately 30% compared to single-wall log construction. The thermal mass stones extended useful heating time by 4 to 5 hours beyond active combustion. The raised hearth platform reduced the volume of air requiring heating while improving heat distribution to occupied spaces. Jakob Müller, whose German masonry experience included work on heated buildings, visited Sam's cabin during a March thaw and recognized the sophistication of the thermal management system. European buildings often incorporated massive stone or brick heating elements called Kachelofen that stored and released heat gradually, but these required specialized ceramic tiles and complex internal flue systems. Sam had achieved similar results using local materials and frontier construction techniques, adapted from multiple cultural traditions. The performance difference became quantifiable during a week of fluctuating weather, when daytime temperatures reached 30 degrees above zero, but nighttime conditions dropped to 10 below. Sam's enhanced system maintained interior temperatures between 42 and 48 degrees using 1 cord of wood for the entire week. Neighboring cabins with conventional designs required nearly 2 cords to achieve interior temperatures that ranged from 28 to 42 degrees, demonstrating the compound benefits of addressing multiple heat loss mechanisms simultaneously. The success of Sam's thermal envelope modification spread through Pine Ridge as neighbors observed his consistent comfort levels and reduced wood consumption. The integration of Scandinavian air gap construction, Ojibwe thermal mass techniques, and Sam's own innovations in heat positioning created a comprehensive system that challenged every assumption about frontier heating. What had begun as an experiment with fireplace design had evolved into a complete reimagining of how buildings should manage heat in harsh climates. By late 1883, Sam's heating innovations had solved the fundamental problems of heat generation and retention, but Pine Ridge faced a different challenge that revealed the hidden costs of inefficient combustion. Margaret Schmidt's husband had built their large hearth according to traditional specifications, and by December they were dealing with maintenance problems that threatened to make their cabin uninhabitable. Thick soot accumulation covered the firebox walls after just 6 weeks of regular use, while creosote buildup in the chimney created dangerous fire hazards that required professional cleaning 3 times in a single season at $2 per service call. The Schmidt hearth demonstrated what happened when incomplete combustion met poor airflow management. Their deep firebox, measuring 18 inches from front to back, placed burning logs far from the room opening where oxygen supply became restricted. Wood burned incompletely in the oxygen-starved environment, producing heavy smoke laden with unburned carbon particles that adhered to cool masonry surfaces. The wide throat opening allowed these smoke particles to condense on chimney walls as temperatures dropped, creating the sticky creosote deposits that posed both fire and health risks. Sam experienced similar problems on a smaller scale despite his superior heat output. During periods when he banked fires low for overnight burning, occasional backsmoke episodes filled his cabin with acrid fumes that forced his family to open windows, even in sub-zero weather. The backsmoking occurred when cold outdoor air descended through the chimney and met rising warm gases, creating turbulence that reversed the normal draft flow and pushed smoke into the living space. Jakob Müller, whose German masonry background included work on complex heating systems, suggested a solution based on European fireplace design principles. German builders constructed what they called a Rauchfang, or smoke shelf. a horizontal ledge built into the throat area that deflected cold downdrafts while maintaining smooth upward flow for hot gases. Miller explained that this shelf created a separation zone where descending cold air encountered rising smoke, forcing the cold air to flow around the obstruction rather than mixing with and disrupting the combustion gases. Sam implemented Miller's smoke shelf concept by building a shallow horizontal step, approximately 4 inches deep, directly above his fireplace opening. The shelf projected into the throat passage at the precise point where the firebox narrowed into the smoke chamber, creating a physical barrier that intercepted downward air movement. Above this shelf, he installed a throat plate made from fitted stones that further controlled the flow transition between the firebox and smoke chamber. The engineering principle behind the smoke shelf involved fluid dynamics that frontier builders rarely understood. Cold air descending through a chimney has greater density than hot combustion gases rising from the fire. When these air masses meet in an uncontrolled throat, they create turbulent mixing that disrupts draft and can reverse flow direction. The smoke shelf forces the cold air to follow a longer path around the obstruction, allowing hot gases to maintain their upward momentum while gradually warming the descending air until thermal equilibrium eliminates the backdraft condition. White pine contributed additional insight about improving combustion efficiency through better air circulation around burning logs. During his winter hunting expeditions, he had observed that fires built on elevated platforms burned more completely and produced less smoke than fires placed directly on the ground. The elevation allowed air to circulate underneath the fuel bed, supplying oxygen to the entire combustion zone rather than just the exposed surfaces. Sam adapted this principle by constructing a raised grate system using iron bars spaced 2 inches apart and elevated 3 inches above his hearth floor. The grate supported burning logs while creating an airspace beneath that drew oxygen from the room through gaps between the fire bricks. This under-fire air supply ensured more complete combustion of wood gases and reduced the production of smoke particles that would otherwise condense as soot on chimney surfaces. The improved air circulation had measurable effects on fuel consumption and maintenance requirements. Wood burned more completely on the raised grate, extracting greater heat energy from each log while producing less unburned residue. Sam found that he could maintain equivalent heat output using approximately 15% less wood than his previous floor-mounted fires, while soot accumulation on his firebox walls decreased to less than 1/4 inch after 6 weeks of continuous use. Miller introduced a third innovation drawn from European masonry traditions: surface treatment of fire bricks with lime ash coating to reduce soot adherence and improve heat reflection. German builders applied thin layers of lime putty mixed with wood ash to the interior surfaces of combustion chambers, creating a smooth, slightly alkaline coating that resisted soot buildup while reflecting more radiant energy into the room. The lime ash mixture required careful preparation to achieve proper consistency and adhesion. Sam mixed 1 part quicklime with 3 parts clean hardwood ash, adding water gradually until the mixture achieved a paint-like consistency that could be applied with a brush made from pine boughs. The coating dried to a hard, slightly glossy surface that reflected firelight effectively, while creating a chemical environment that discouraged soot particles from bonding permanently to the brick. The performance improvements from these combustion refinements became evident during Sam's first extended test in January 1884. Over 12 continuous hours of burning, his modified system produced less than 1/2 inch of soot accumulation on the back wall compared to 2 full inches in comparable standard hearths. The reduced maintenance meant that Sam could operate his heating system for an entire season without requiring professional chimney cleaning, saving $6 in service costs while maintaining superior performance. More importantly, the complete combustion achieved through proper air circulation and smoke management eliminated the acrid backsmoking episodes that had plagued his earlier attempts at overnight heating. Sam could now bank his fires confidently for 8-hour burns without risk of smoke infiltration, allowing his family to sleep through cold nights without interruption while maintaining steady interior temperatures. The fuel efficiency gains were equally significant. Sam's refined system extracted more heat from each cord of wood through complete combustion while losing less energy to maintenance problems and draft disruptions. His total seasonal fuel consumption dropped to approximately 8 cords compared to the 12 to 15 cords required by conventional hearths of similar size, representing cost savings of $20 to $35 per winter at prevailing wood prices. The integration of smoke shelf technology, raised grate combustion, and treated brick surfaces created a complete combustion management system that addressed every aspect of fuel efficiency and maintenance reduction. Sam had transformed his experimental narrow opening hearth into a sophisticated heating apparatus that outperformed conventional designs in heat output, fuel consumption, and operational reliability while requiring minimal maintenance throughout the heating season. The winter of 1884 arrived with a vengeance that tested every assumption about survival on the Minnesota frontier. Beginning in late January, a high-pressure system settled over the Great Lakes region and refused to move, creating a cold snap that lasted 14 consecutive nights with temperatures below minus 15 degrees Fahrenheit. Sustained winds reached 50 miles per hour across the open prairie west of Pine Ridge, driving wind chill factors down to levels that made outdoor work impossible for days at a time. The brutal conditions coincided with supply disruptions when heavy snow blocked the main road from Duluth, delaying wood deliveries by more than a week just when fuel stockpiles reached critically low levels. The settlement's conventional heating systems failed catastrophically under conditions that demanded maximum performance with minimum resources. Thomas Brennan's family abandoned their main room entirely, retreating to a single bedroom where they huddled under every blanket they owned while their large hearth consumed wood faster than they could feed it. Despite burning continuously, their cabin's interior temperature dropped to 20 degrees Fahrenheit on the coldest nights, forcing them to wear full outdoor clothing inside their own home. The Schmidt family faced an even worse crisis when thermal stress cracked their chimney foundation, allowing cold air to pour directly into their living space through gaps in the damaged masonry. Margaret Schmidt measured interior temperatures of 18 degrees at dawn, despite having burned through 2 full cords of emergency wood purchased from neighbors at the inflated price of $8 per cord. The repair costs for their damaged chimney would eventually reach $75, nearly half their annual cash income from the small farm operation. Across Pine Ridge, families burned through their carefully planned fuel supplies at rates that threatened financial ruin. The Anderson cabin required 3 cords of wood just to maintain interior temperatures in the mid-20s, exhausting their winter stockpile by early February. Jacob Muller, despite his masonry expertise, struggled with a conventional hearth that consumed wood so rapidly that he borrowed money from the settlement's informal credit system to purchase additional fuel at emergency prices. Sam's integrated heating system faced the same merciless conditions, but responded with the resilience that came from addressing every aspect of thermal efficiency. His narrow opening hearth, enhanced with smoke shelf technology and raised grate combustion, generated maximum heat from each piece of fuel, while his thermal mass stones extended that heat through the long sub-zero nights. The double wall construction with air gap insulation protected against wind-driven infiltration, while the raised hearth platform concentrated warmth in the occupied living zone rather than trying to heat the entire cabin volume. The performance measurements during the 14-day cold snap revealed the compound benefits of Sam's systematic approach. His cabin maintained interior temperatures between 36 and 40 degrees Fahrenheit throughout the crisis, comfortable enough that his family slept without heavy blankets and conducted normal daily activities. Total fuel consumption for the 2-week period reached exactly 4 cords of split hardwood, compared to the 6 to 8 cords consumed by neighboring cabins that achieved far less comfortable conditions. The economic advantages extended beyond simple fuel savings. Sam avoided all repair costs during the brutal weather, while conventional hearths suffered various failures that required expensive professional attention. His clean burning combustion system eliminated the need for emergency chimney cleaning that cost neighbors $2 per service call. The reduced maintenance requirements meant that Sam could focus on productive activities rather than constant fire tending and equipment repair. More significantly, Sam's system maintained consistent performance throughout the crisis without requiring the desperate measures that other families adopted. While neighbors burned furniture, fence posts, and even structural lumber to maintain minimal heat, Sam's efficient combustion extracted sufficient energy from his planned fuel supply to maintain comfortable living conditions. His family continued normal routines of cooking, reading, and household tasks while others struggled simply to survive. The social impact of Sam's success became impossible to ignore as Pine Ridge emerged from the cold snap. Anders Johansson, who had initially ridiculed the narrow opening concept, quietly approached Sam about modifying his own hearth design. The Swedish carpenter had burned through his entire winter fuel supply and borrowed heavily to purchase emergency wood, making him receptive to any approach that promised better efficiency. Margaret Schmidt, whose family had suffered through 18-degree nights while Sam's cabin remained comfortable, asked detailed questions about thermal mass installation and smoke chamber construction. Her damaged chimney required complete rebuilding, creating an opportunity to implement Sam's proven techniques rather than simply replacing the failed conventional design. The local supply agent, who had dismissed Sam's modifications as excessive frontier fussing, began taking orders for masonry components that matched Sam's specifications. Two families requested narrow opening fireboxes with large smoke chambers, while three others inquired about raised grate systems and thermal mass installations. The agent's spring inventory included limestone slabs, sized for hearth applications, and iron grating materials that reflected growing demand for Sam's innovations. Word of the Pine Ridge heating experiments spread through the regional network of timber camps, trading posts, and settlement supply operations. By summer 1884, masonry contractors in Duluth and St. Paul reported requests for shallow fireboxes with controlled openings rather than the traditional deep caverns that had dominated frontier construction. The practical advantages of fuel efficiency and maintenance reduction appealed to cost-conscious settlers facing the economic realities of harsh climate survival. Edward Clark, a regional building inspector who documented construction practices across northern Minnesota, visited Pine Ridge that autumn to examine Sam's heating system. Clark's subsequent report to the Territorial Building Commission noted that properly designed small opening hearths with thermal mass integration achieved superior performance compared to conventional large cavity designs. His recommendations influenced building codes and construction standards throughout the Great Lakes region. The vindication of Sam's approach represented more than technical validation. It demonstrated how traditional knowledge from multiple cultures could be synthesized to create solutions superior to conventional frontier wisdom. The Scottish masonry techniques, Ojibwe thermal management principles, German combustion innovations, and Scandinavian envelope construction methods had combined to produce a heating system that outperformed standard American frontier practices in every measurable category. The legacy of Sam's innovations extended far beyond Pine Ridge, influencing regional building practices and contributing to the gradual recognition that bigger was not necessarily better in frontier heating design. The principle that controlled combustion, proper thermal management, and systematic efficiency improvements could outperform brute force approaches became foundational to modern building science, validating the cross-cultural wisdom that Sam had quietly assembled in his Minnesota cabin.